All right, so I'm going to go over the 7B problems. I'll show you my key and sort of provide an explanation, especially for the trickier ones. So looking at these three problems, they involve this differential equation, dy dx equals x times y cubed. The three problems, first one wants you to make a slope field. The second one wants you to find the second derivative using that first derivative, and then talk about the concavity of the original function. Keep in mind that there's some original function that they're not showing you. There's a y equals f of x, and then that's actually what they want you to do in the third part of the problem is to solve for what that original function is. So by the time we're done, we'll have the original function through that spot. We already know its derivative. We'll also know its second derivative and have a slope field of it. All right, so finding the slope field should look something like this. Basically, you're going to take each one of these points and just plug them into this derivative. So, for example, how I'm getting the slope here is this is the point 1, 1. I plug x is 1 and y is 1. 1 times 1 cubed is 1, and I know to make the slope here 1. And the slope of 1 is about 45 degrees here. I should say it's exactly 45 degrees. And you do this for every single point. So all the points that have 0 in their coordinate, which are all of these and all of these, they should come out flat. So on this problem, they gave 1 point for getting all the 0 slopes, and then you get 1 more point for the other slopes. So showing that this is -1, and this is -1, and this is +1, this is +1. So if you get this picture, it's a total of 2 points. Then they want the second derivative. So you need to take that original derivative equation. So the original derivative equation was dy dx equaled x times y cubed. You need to take the derivative of it again. Remember, this is the Leibniz notation for taking the derivative with respect to x. So if you take the derivative with respect to x of the fact y already has its derivative, take it with respect to x, the derivative of the derivative gives you the second derivative, and this is the Leibniz notation for that. So d squared y over dx squared means the second derivative. Now, what actually is the value of the second derivative based on this function? Well, because this is a product of functions, you can take its derivative, but you have to use the product rule. So the product rule says you take the derivative of the first one times the second, and then add it to the first one times the derivative of the second. Now, when you take the derivative of x, you get 1, leave y cubed alone, put plus sign, leave x alone, and then the derivative of 3y is 3y squared, but since the variables don't match, if the variable doesn't match, like here, so this is in terms of y, you're taking derivative in terms of x, you need to use the chain rule. So anything that doesn't have a matching variable pops out this factor of dy dx. This is basically the chain rule, find the derivative of the inside. We don't really know what the inside looks like, so this is just a symbol for it. So this is the derivative of that with respect to x. Once you get this, you need to get rid of this derivative here. Basically, what is dy dx? They told you that in the original problem. Remember, dy dx is this thing. So I'm replacing dy dx with xy cubed, and then that gets simplified. You can take this, multiply these together, you get y cubed plus 3x squared y to the 5th. Now in this problem, getting this far gets you a point. If you forget this dy dx or don't use the product rule, you can't get any points for this problem. So using the product rule and doing the replacement, at the very least this line here gets you the credit. So then they ask about, in the end part, so give a reason for your answer. Basically, they want you to determine the concavity for the original function based on quadrant 4. So since this is the second derivative tells me about concavity. Positive second derivatives mean concave up, and negative second derivatives mean concave down. Now, we can show that in quadrant 4, this thing's always negative. It's basically in quadrant 4, x will always be positive and y will always be negative. That's how you have a point in quadrant 4. You have to go to the right and down. If you plug these into the equation, any positive number squared will stay positive. So this whole part will be positive. I'm circling the 3x squared. However, negative numbers, if you take a negative number to the 5th power, it becomes negative. So this whole term, the entire thing that I'm circling here, will become negative. And then this part will also be negative. Since this number is negative and you're adding a negative number to it, for any point in quadrant 4, this expression is always negative. And since this thing's always negative, and it's the second derivative, when the second derivative is negative, that implies that the original function there that you're not seeing a picture of, the original function, since it's always negative in that quadrant, implies that it's always concave down. So this kind of reasoning and explanation gets you the second point. All right. So in the last part was solving the differential equation, and that's the tough part, and it's worth most of the points in this problem. So to solve this differential equation, it's a separable differential equation. Separable means you can move all the y's to one side and all the x's to the other. So to move this y cubed over, you want to divide the y cubed to the other side, and to move this dx, you want to multiply the dx. That gives you this. Just separating the variables always gets you a point on a differential equation. So this right here is 1 point. To get the next point, or 2, you need to get the antiderivatives of these. So the antiderivative of x, remember it's antiderivative, so you're going to use the power rule backwards. You're going to add 1 and divide by the new power. You get 1/2 x squared. I'm putting the plus c on this side because in the problem, they say to get y by itself. So I don't want to put the c over here and have to move it later. So I'm going to put the c with the x squared. This doesn't need, this one here doesn't need the plus c since I've handled it over here. The antiderivative of this, be careful, because when I was looking at it, a lot of people thought this was natural log. Be careful that it's only natural log if it's to a power of -1. So this thing being the denominator, you have to turn it to y to the -3 and then use the power rule on it. It becomes -1/2 y squared. So there's 1 point for the antiderivative of y. There's 1 point for the antiderivative of x. So getting here gets you 3 points. Now how do you do the rest of it? Well, they gave you the point to plug in. They gave you the initial condition. So they tell you in the problem, f of 2 equals -1. So what I'm going to do is use that to find c. If I plug in 2 for x, I should get out -1 for y. And solving this, if you're careful, you can go through and get that c is -5/2. That's a point. So far we're 4 out of the 5 points. The last thing is to get y alone, because in the problem they say they want the solution as y equals f of x. So they basically want y by itself and the function in terms of x that you get. So talk through that. Basically from here, I'm going to plug in the c value. Since it was plus c, c is -5/2. I'm going to have -5/2. Now I just need to get this y alone. To do that, it's in a denominator. I'm going to try to flip both fractions, but I need this to be a fraction first. And since these have a common denominator, this is x squared over 2, 5 over 2. I can subtract the tops and put them over 2. So I get -1 over 2y squared equals x squared minus 5 over 2. Now what I'm going to do is flip them over. So if I flip this one over, it's, well, I also got rid of the negative, so let me do that at the same time. Let's see, let's follow the arrow here. So I'm going to go this way because I did it a couple different ways for my key here. So I'm going to follow it this way. I got rid of the negative before I did the flipping. So to get rid of the negative, basically I could multiply by -1 or divide by -1 on this side. That'll make it positive. If I make this negative, it's basically going to just affect the top. By making the top negative, if I make this negative and negate this, it'll basically flip it around. So I rewrote it as -x squared and +5, so it's this way. So this is getting rid of the negative. Now since they're both fractions, I can just flip them both over. Reciprocate this, I get 2y squared. Reciprocate this, get 2 over 5 minus x squared. And then I divided the 2. When you divide the 2 over, that 2 cancels, so you get y squared equals 1 over 5 minus x squared. And then you got to square root the thing. Now when you square root the thing, you get y equals, but you get plus or minus the square root. You have to choose the right one. How do you know which one to choose? Well, that point, remember, has to work. When you plug in 2, you have to get out -1. The problem with this is if you choose the wrong one, say you pick the positive version. If you pick the positive version of this, when you put in, I remember what the number is, 2. If you plug in 2 here, if you leave this positive, it comes out as positive 1, and it's not supposed to. It's supposed to come out as negative 1. So you need the negative sign, you need the negative version of this. Basically, there's the positive version of the curve up top and the negative version of the curve on the bottom. The negative version of the curve will have it, if you plug in 2, it'll pump out the correct value, which is negative 1. So basically, when you do the plus or minus of the radical, make sure that you use the right half of it. The right half is the negative half because it allows me to get out negative 1. All right. So that's the last point, and that's pretty tricky. All right, so that's that problem. That's how you can get all the points on it. The second problem they included had this pretty tricky differential equation. This is one of the more difficult ones I've ever seen to have to try to solve. But basically, they give you this differential equation. They give you this slope field. So we need to fill in the solutions on the slope field. That part should be easy. They want me to get the equation of the tangent line. That, if you understand how to do the tangent line, it's not that bad, but it's not worth that many points either. Again, tangent line is usually just a point because it has to do with finding slope. And then once again, you have to solve the differential equation at a certain value. So it's similar to the other problem, but it's actually a little more difficult just because this differential equation is a little trickier than the other one. So starting off, to just get the slope field through the 2 spots, basically, they used this differential equation at all these different spots to get what the slopes were, and it traces out this sort of funky field here. If you want the solution through 0, 1, you're going to go to 0, 1. They even put the dot there for you. So you're going to go here, and you're just going to follow the current. Well, since this thing's flat to the left and right, the answer is just that flat line. So if you throw in that flat line, there's your solution curve for 0, 1. Solution curve for 0, 5 over 2. Well, 5 over 2 is 2 halves, 2.5. They put the 2.5 dot there. You just have to now, from here, follow the curve. So just sketch, as close as you can to those. So that's on the right side. And on the left side, be careful because you're going to sketch it. You're going to come up here, and then it does abruptly turn around. So in between here and here, it wants to get flat. So as it keeps going, you don't want to just keep going up. If you follow it, it sort of takes you into one of these that flattens out and then turns you back around. So roughly, that's what it looks like. So they actually gave you a point for each one of these curves. So this is 1 point. This is 2 points. Now we need to get the tangent line. So let me show that. So to get the tangent line, here's the equation of a line. The tangent line needs to go through the point that they give you, and it needs to have the correct slope. So the point they gave you in the problem, they tell you the point is 0, 5 over 2. The key is getting the slope. The way you're going to get the slope is you have to plug, what's the slope is the derivative. The derivative has x and y's in it. If you plug in x and y, you'll find out what the slope is, and then you'll be able to fill it into the line. So basically, what's the slope? It's the derivative at that spot. What's the derivative at that spot? We'll plug in 5 halves for y and 0 for x, and then just go through and solve this down. The trig here, make sure this cosine, don't distribute the cosine. Just find out what this inner number is. This inner number comes out as pi, so we need cosine pi. 0 plus 1 is 1, and 5 halves minus 1 is 3 halves. Cosine pi is negative 1. So if you multiply negative 1 times 3 halves, you get negative 3 halves. That's the slope. So what you got is the spot you're going through and the slope at that spot. So the tangent line to whatever function this is, the tangent line will look like this. Basically, plug in the point and plug in the slope. So the slope was negative 3 halves. The point was 0, 5 halves. And you can just leave it this way. You can simplify if you want, but I wouldn't risk it. Just leave it like this. That gets you a point. All right, so we're up to 3 points. The rest of the points come from solving the differential equation. This is one of the more difficult ones. So to solve this differential equation, once again, it's separable. So separating it is necessary. Here's it separated. Just to go back up here. To separate, you're going to divide this y minus 1 over and multiply the dx with all these x's. So when I did that, here's my 1 point for the separation. I get 1 point for doing this. Now, to get the rest of the points, I have to integrate both sides, and both of these need a u substitution. This one's simpler, but this one's pretty complicated. So basically, they're going to give you a point for doing the antiderivative of the left side, the antiderivative of the right side, and the fact that it needs a U substitution, they gave an extra point for that. It was for this complicated one over here. So let's look at each side separately to get the antiderivative of this side. Technically, I need a U substitution because this is like a function of a function. It's simple, but it is what it is. So y minus 1 is going to be my u. Then du is going to be the derivative of this. So the derivative of y is 1 dy, and then the negative 1 is going to go away. So du is actually just dy, which is nice because when I go to replace these, 1 over y minus 1 is 1 over u, and dy and du are the same, so I can just replace them out. Now it's all in terms of u. 1 over u, that antiderivative is natural log of absolute value. So this is basically u to the negative 1. This one comes out as natural log. So this is natural log of absolute value of u. Technically it's plus c, but I'm going to put the plus c on the other side. And what was u? U was y minus 1. So the antiderivative of this is natural log of absolute value of y minus 1. On this side, this one's complicated because basically notice that this is a function of a function, and this little extra multiple is sitting here. So when you do the u substitution, it's going to absorb everything. I'm going to make u the inner part here. So u is x squared plus 2x plus pi. Du is the derivative of that, which is 2x. So this thing gives you 2x. This thing gives you 2. Pi is a number, so pi's derivative is 0. And then you have to spit out the little dx. All right, so du is 2x plus 2 dx. Now, how am I going to do the u substitution? Well, this thing was my u, so I get cosine u. All right, so I have that there. I need to get rid of this x plus 1 dx because that's still sitting here, the x plus 1, the dx. So what I'm going to do is, since I need 2x plus 2, I'm going to give this the 2. If I give this the 2, I have to compensate by putting that 1/2 on the outside. Remember, it's illegal to just throw it in here. But if I put a 2 on the inside and 1/2 on the outside, that's fine. So what I'm going to do is throw that 1/2 out there, throw the 2 in here. This makes 2x plus 2 dx. So since this is 2x plus 2 and this is dx, all of that can be replaced with du. So this part and this part together are du. So now everything's in terms of u. So this whole thing's equivalent to 1/2 the integral of cosine u du. If you can get that far, this is easier because cosine u's antiderivative is sine u, and u was that big chunky thing. So in the end, when I go to replace it, so I get 1/2 u plus c, so I get 1/2, or so 1/2 sine u plus c, so I get 1/2 sine, that chunky thing. All right, so that's getting me 4 points. Now the rest of it is, this is the left side of the equation, this is the right side of the equation. I need to find c, and then I need to get y alone. So a point for finding c. To find c, this is the left side, this is the right side. What's c? We'll plug in 0 and plug in 5/2. So when I plug in 0, I get sine pi, and sine pi is 0. So this whole thing zeroes out, and all I'm left with is c. On the right side, I'm stuck with a yucky number because I get natural log of 5/2 minus 1, which is natural log of 3/2. So c is actually natural log of 3/2. So now I'm going to take this equation, replace c with natural log of 3/2, and it doesn't take that much more to get y by itself. Even though this looks really ugly, just keep it the way it is. The way you're going to get rid of natural log is to do e to this power will equal y minus 1. So notice I wrote that e to that power here. This is going to all be in the exponent now. E to this power equals y minus 1. All I have to do is add the 1 over, and that's my point. You could simplify this further, but you don't have to. Now that y is by itself, the answer is y equals e to this really ugly power plus 1. And like I said, it's not very easy to do, and it's not very easy to know this is the answer, but it is. All right, so that gets you the last point, and that's this entire problem and the last problem explained. So hopefully this helps you know how to get all the credit on these. Like I said, I would gauge, just to give you a difficulty, there's very easy and very difficult things in both problems. So to just recap scoring, this is considered really easy and got you 2 points. This is a little harder, but something that they ask a lot. This is the most difficult thing, solving the equation. Same thing here. Sketching these in should be 3 points. It's very easy. Once again, one on the tangent line, a little harder, but they ask it a lot, so know how to do it. And then this was very difficult. So I said most people would not get through that unscathed. So if you're able to get that perfect, you're definitely capable of getting a 5, at least if they give you a question like this. All right, that ends this going over problem 7 there. So hopefully that was helpful. See you next time.